Is
Yes.
this visible now? Okay.
Yes.
Yeah. Okay, we can start. Yeah.
Thank you, Professor. Good evening, everyone. Welcome to the network seminar series hosted by the Center for Networked Intelligence at the ECE and RBCCPS IISc. It's my pleasure to introduce today's speaker, Professor Rijurekha. She will be speaking on creating datasets for environmental sustainability problem in developing countries. Professor Sen is an associate professor in the Department of Computer Science and Engineering, IIT Delhi. Before joining IITD, she was an Humboldt postdoctoral researcher at Max Planck Institute for Software Systems. She works in the area of cyber-physical systems and uses interdisciplinary computer science methods for applications at the intersection of information theory, technology, and society. She completed her PhD at IIT Bombay in 2013 and worked as a research fellow in SMU Live Labs from 2013 to 2014. Her dissertation on automated road traffic monitoring in developing regions was awarded the ACM India Doctoral Dissertation Award 2014. The audience is encouraged to ask questions at any point during the talk. Questions can either be asked by unmuting and speaking directly or typing them in the chat box from where they will be relayed to the speaker. Over to you, Professor.
Okay, thank you very much for giving me this opportunity. I have visited the Robert Bosch Center, as part of my job talks, and my work is very closely related, I would say, to that lab. So I'm happy to present what I have been doing here and look for opportunities for future collaborations as well. So when I say creating data sets to study urban sustainability problems, these come in different through different opportunities. For example, road traffic, which I have been working on since my PhD. I would say this is more or less standard now that the traffic police would want to monitor a large parts of the city. For example, in Delhi-NCR, almost all of Delhi, Noida, Gurgaon, we have working collaborations with the Delhi Police and other similar organizations, where they would give out these challans to the vehicles and also do some kind of other monitoring and infrastructure development. And typically the way it would go out is calling for open tenders or bids and saying that these many police intersections need to be now monitored using road cameras along with computer vision software. And typically, as an IIT Delhi professor, I would be in some committee to see the end-to-end process, that how the call for tender or the call for proposal goes out, how the proof of concept actually is demonstrated in certain intersections, like what is the accuracy, what are the latencies, what kind of network infrastructure the companies are providing. And then I'll have to give them marks based on the technical capability and things like that. So there, the data sets are continuously being generated based on the available bandwidth or the local storage at the roads which are available, or may in the ICCC, which are the command and control centers. And there are umpteen opportunities to do computer vision kind of work there. So for example, this is a typical setting in Delhi where the cameras would be placed either looking into the intersection or away from the intersection. And I'm sure that there are similar such settings in Bangalore traffic. And typically these will be doing speed violation detection or signal violation detection in real time, and also ANPR to give the challans. But even in the long run, that what is the flow through that particular intersection? If we don't even want to run deep neural network models in real time, even just with simple background subtraction, we can detect that this queue building up, and then when the signal turns green along this axis, I hope you can see my mouse, the queue length starts coming down, and again when the signal turns red, the queue starts building up and again coming down. And this is just based on the traffic density using some simpler vision algorithms like optical flow or background subtraction, which can even run on small CPUs like the Intel Atom CPU, which is a industrial quality board which is put up, whereas There are also heavier GPU processes which can also run for detecting the vehicles themselves, detecting their number plates, as well as all the other rule-based heuristics which are there. And in the long run, for example, here I am showing along this x-axis the hour of the day, and each of these three plots is for one approach. So this is a three-way intersection where there are three roads. So instead of having these four approaches, there are three approaches in Lajpat Nagar intersection. And as we can see, the traffic density in the early morning hours, this is the morning peak, and then it comes down, and then again it goes up. Whereas another approach does not see any significant peak at all during the day, any time of the day. And this is the third approach, which does not see a morning peak and only sees an evening peak. And this is collected over 40 days, and this actually is getting collected and monitored over months and years to build a statistic of how actually the flow of traffic or the volume is changing across these roads and intersections, right? So we will see what is the use of this kind of data for my PhD students and other computer science researchers eventually in the talk. Here I'm just setting up the context of how data sets are being created, being labeled and stored, and in collaboration with whom. So this particular traffic example is with the traffic police and of the different jurisdictions. The other kind of data set is more research oriented, and there is no direct kind of revenue to be earned, unlike the Chalan scenario with police. So this is for example, the pollution or PM 2.5 data sets, which many groups across India have been collecting, including our group. And in this particular case, we will have to build these instruments. This is one of the requirements, because the government instruments are worth crores of rupees, and there are only 7 or 8 of them in Kolkata, in the city of Kolkata in West Bengal, around 35 to 40 in Delhi-NCR, which is like really a very small fraction of what the total area of the city is. So one example work here is these monitors, along with placing them in schools, colleges, in other places. We also mounted them in public buses, which traverse across the city for almost 16 to 18 hours every day. And they are kind of this moving monitors, and the buses also stop at different places, at the different intersections they stop, at the bus depots they stop. So there is significant amount of PM 2.5 readings which the buses can collect at road level, at which the commuters breathe. So it is not at the very large heights in which the CPCB towers kind of place their monitors. These are at the more ground level and computer level, what they're breathing there. And of course, for these, the collaborations need to be built up with either, for example, DPCC, which is the Delhi Pollution Control Board, or in case of West Bengal, it is the West Bengal Pollution Control Board, and sometimes also with the bus ministry or the transport ministry, because it is their infrastructure or the fleet which we are instrumenting. Unlike the traffic police and the cameras which are on the road, these are the moving buses, right? So this is some set of kind of collaborations and data set collection. And as a result of this kind of instrumentation, for example, we can keep running these kind of networks. And because this is more research driven, these are typically not funded by the ministry themselves or the pollution control board, but as a professor, I'll have to get my own research grant. So in Kolkata, for example, the EDF, which is an American very well-known company, who also had funded the first Google Air car, which was a vehicle instrumented pollution carrying car. So this Environmental Defense Fund, EDF, had funded this project. So it is kind of the funding comes from somewhere, the research questions are raised by us, and then the Pollution Control Board, the Transport Ministry, they become partners where they say, yes, you can do this work. And they also help in getting us install low-cost sensors along with the CAQMS unit. So this is very important for the calibration purposes, that the low-cost instruments, I'm showing this plot here for reference in Kolkata. The orange graph here shows the daily high pattern as measured by the low-cost sensor, because in Kolkata, the relative humidity is very high. So the low-cost sensor would measure a higher value because the particles might be absorbing this water vapor, and there is no heating element, unlike the high cost instrument as told by the CPCB. So there needs to be some ways of co-locating our low cost sensor with CPCB sensors, which we do with every CPCB sensor in the city, and then learn this calibration parameters with respect to temperature and relative humidity, so that the higher reported values can be corrected and calibrated. So in these, both for instrumenting buses, for putting up sensors co-located with the CAQMS units, we need this help from the local pollution control authorities. And a third kind of data set also is, I show an example of also related to breathing. So this is also pollution, but this is a very workplace generated pollution. So this is, we are doing a lot of work in Rajasthan, where marble workers kind of work their, the stones to build the Akshardham temple and other bigger temples. And as a result of this inhaling whatever fumes are being produced while they work, they get calcification of their lungs, and that's around 35 to 40 years of age. They are not able to work anymore, and it's a slow kind of very painful degradation of health. So this is actually, which it came to us from Rajasthan government, because they have to pay compensation money to these families who are kind of reporting cases. So they wanted a monitoring network to see how much are they breathing because of what kind of stone working activity, and whether we can build a lower cost sensing, because you cannot put a crore rupees instrument in every marble workshop. So this is also work being done. There are some NGOs on the ground who help us working among the workers. So these are different, each of them is a very different ecosystem, where we have to understand the stakeholders, that who are the people who are interested in this problem, who has the money, where will the data go, what kind of instruments can we use, and depending on the exact scenario, we'll have to kind of build the end-to-end system for data collection, analysis, argue about the reliability of the data, correct the data, and stuff like that. So, given this context, now I'll move to this more computer science, because that's the department I belong to in IIT Delhi, kind of research questions. So I divide that into three parts of work. So one is the sensing itself, that what to sense and when to sense, or what, like where is to put the sensor itself. Becomes a research question sometimes, because the main problem here is we always work under budget constraints. So it cannot be that we will put up thousands or millions of sensors, and it is also sometimes quite unnecessary. To even figuring out that what to do at what point of time is our interesting question. So I'll start from there, and then we'll look at how to secure these devices, because these are very sometimes sensors which I'm placing on traffic signals and asking them to control the signal. So these are safety critical aspects. Also collecting a lot of data which might sometimes have some privacy implications, especially the worker kind of data. What are they doing all day? If there is no privacy for the worker as they're working, that won't be good. And finally, I'll talk about this edge computing, which in IISc also there are very strong research going on. And this is because network is not ubiquitous in India. So transferring all data for processing from a Rajasthan marble workshop to the cloud is sometimes not feasible. So we sometimes have to locally process the data and then only send some relevant portion or useful portions of the data. So I'll talk a little little bit about this edge computing part. Okay. So first the question I'll talk about is where to sense, and I'll take the example of air pollution sensing here. So when we initially collected data from Kolkata, these are some of the graphs which we saw. So this is a particular a day. So the hour of the day is shown here, and this is another day, and the hour of the day again is shown on the x-axis. As we can see, each of these lines which are here belongs to a different sensor, right? And these are our low-cost sensing units, and the sensor numbers are mentioned here. So what we see is for each of these sensors has a high peak here and it comes down, and this is followed by sensors all across the city. Because if you look at these numbers, some of them might be very much in the north of Kolkata and some of them might be very much in the south of Kolkata. So the entire city is seeing some sort of regional pattern, right? It might be because of the weather of the city, the rain it sees, the external factors around Kolkata, which is sending pollutants to the city. So whatever is the base level of pollution there, for these reasons, there is a certain regional pattern which is observed, which all the sensors across the city are seeing. And this is also true on the other day, where the pattern might be different, that the values are lower in the early parts of the day and then they peak up and they again somehow come down. But all the sensors somehow followed a certain trend, right? So this is the discussion we had with the pollution control board, that if the entire city is seeing something, is it really important to sense more, or is it because the city's average can be captured very easily with a very few sensors, which anyway the city is doing, randomly placing maybe 6 or 7 high cost crore rupees sensors. So we then decided to look a bit deeper into the data. And what we figured out was there were some hyper local patterns as well. So this pink line, for example, it always came up at the top. So if we collected the data over 1 year, and almost every day there was this strong regional pattern, but this pink line, which belongs to this S22, and this S22 is actually near this very busy intersection, traffic intersection. So even though this particular sensor is following the trend of the city, its absolute value every day is much higher than its other counterparts in the city, right? So the people there or the commuters there will be inhaling more value of PM 2.5. And similarly, the brown line here always came down. I'm just showing by example, not the statistical significant results, because this is more intuitive to see. So the brown line always comes down at the bottom, and the brown line is actually this sensor, which is near this water body. So there might be some local sinks of air pollution, which brings down things locally. And this is such a location where this natural water body is helping in reducing the pollutant level. So this is the absolute value in terms of deviating from the regional pattern. And the other thing was this hyperlocal pattern. This a graph is an example, and this is another example where every day at a particular time of the day, the sensor might see a very high peak. So this we figured out was because of some local commercial activity, a food stall or some thing like that, which kind of operates for us within a certain period, right? Sorry, I have a cold and right. So the effect of having these hyperlocal patterns is, I'll show that with some numbers. So here, for example, I am showing this BGFWRS. These are the locations for the CPCB high cost sensor. Okay, so these are the black dots here, which are already in the city of Kolkata. So this first row here, for example, in each of them is the RMSE, or the root mean square error of interpolation from these sensors using only the first three. So we use the value of these three sensors, and then we interpolate for all the locations which are shown along the columns, and this is the value of the root mean square error. And the lower the RMSE, the better it is as a sensing problem. Sorry. Okay. So the lower the value of RMSE, the better is the sensing system. But we see that if we add, for example, this sensor, which is here, let me just move this bar. At this location, this RMSE actually goes up. So I am buying a crore rupees sensor and I'm placing that sensor in this location. And as a result of placing this sensor, my root mean square error of interpolation is actually going up in most of the locations. From 22, it goes up to 45 here. From 19 to 23, here it goes up drastically from 16 to 57. Right, and the whole reason behind this is what we were seeing in the previous slide. This location GH actually has a lot of hyperlocal pattern. So hyperlocal pattern means that this location is actually seeing something which is not seen by anybody else. So therefore, this sensing location is not good to compute an average value for the rest of the city. So this is what we mean as the problem of where to sense. And we formulated this problem for the West Bengal Pollution Control Board. We said that if the Pollution Control Board has a certain budget to put in maybe 5 new sensors or 4 new sensors, the low cost sensor can keep running as a network. And based on the low cost sensor data, the location for the high cost sensor can be determined. Okay, and this is how we formulated this. We said this was the original network of high cost sensor. And then we want to add some candidate locations to that, right? This is the union. And as a result of this, this loss function should reduce or should come down. And we need to pick A from this subset of candidate locations, and the number of A can go up to the budget, right? This is and we should choose these locations such that this reduction in loss is maximized. So initially we have some loss function for this interpolation. This can be a interpolation problem. It can be a pollution forecasting problem. So whatever the machine learning problem is, corresponding to this loss function will change. But the loss function with the original sensors and then with additional sensors, as we are putting in new locations, this reduction in loss, we want to maximize it. Okay, so this is how we formulated the problem. And then this can be solved in many ways. We specifically used some RL kind of active learning to do this. Right? So this is one example of where to sense and formulating a CS problem for that. The other thing was what to sense, right? So I showed this example of these cameras at the traffic intersections, and both fine-grained information was being derived from my lab. That because we had labeled data, we were working with Vehant and Abmatica, which are these computer vision big companies. So we can get classified counts of vehicles. And we can also get just simple density values, right? Just using background subtraction. And what we figured out was in the literature of traffic intersection control, for example, using reinforcement learning or other things, there were very well cited papers from CMU, for example, Presslight and Colite, where the reinforcement learning state size was really huge because they were using information of every vehicle which was there on the road. And of course, these were done in terms of the Western traffic. right? So what we figured out that in India, this accuracy of detecting every car on the road, and it goes down with change in lighting conditions and other things. And actually the kind of metric which the police care about, the traffic police, which is the throughput of the intersection or the average travel times of the cars, those actually can be optimally minimized or maximized. This throughput can be maximized, or average travel time can be reduced or minimized by using much smaller state space. Okay, so this is what we figured out, that we computationally also this is much cheaper. We could run the background subtraction on a CPU, as well as a very small reinforcement learning based engine along with some safety criterion on some 4-core quad-core Intel Atom boards. So we did not need to run the GPU constantly for the purpose of intersection control or the green signal. So here the problem is just the RL is formulated as the state being what is the state of or traffic density on the road, and the actions are whether the green signal has to continue or should shift to the next approach. Right. So what we figured out was this very heavy RL is not needed, and instead we can go with very small RL with very small number of states. And this is relevant to what to sense. Do we need to really count every car and its type for doing intersection control, or a simple density estimation is good enough for Indian roads? Because anyway, this getting the actual count is difficult under different lighting conditions. The other example I want to give is from air pollution, not from traffic. So here I'm just moving around the bar because I had lost it once. So here, this date is November 14th, and I had just joined in 2019 in IIT, and I had started working with this low-cost pollution sensors. So each of these sensor was in the IIT campus, and the last three was in traffic intersections because I was working with the traffic cameras. So I had put up three there. So what we figured out was these are sorted in terms of higher pollution, average pollution seen on that particular day, November 14th, right? So this is average ppm 2.5. And within the campus, we figured out that whatever is near towards the road or near some construction site of hostels in the campus sees a higher value of air pollution, and the traffic intersection sees a significantly higher value. Okay, so this was in Delhi, not in Kolkata. And this is another day, November 18th, when again, the same set of sensors reported values, but much lower compared to November 14. And here also the traffic intersection actually showed higher value. Okay, so this the effect of road traffic is kind of very visible here. But these plots are also very interesting because on this day, November 14th, the odd even rule was actually there in force, which meant that at least some fraction of private vehicles were not present on the road, right? And here the odd even rule was already taken away. It was from November 1st to 15th, and there was no odd even rule on this day. So the number of cars supposedly were more, right? But what we are seeing here is the pollution value is actually much higher with less number of cars, and the pollution value is lower with higher number of cars, which kind of is counterintuitive to what we are observing here. Right here, we say that that intersection because of vehicles is seeing this higher level. In Kolkata, also, I said there was one intersection which always had higher absolute value, but somehow these two plots kind of refute it. So then we had to sense some more, right? We had to get auxiliary information. And what we figured out was the wind speed on November 14th here was actually 1/3 of the wind speed on November 18th. So it was not actually the cause or the vehicles, it was maybe polluting much more, but actually it was a gift from God that the wind was also blowing at three times higher the speed, which blew away all the air pollutants, right? So if odd even was not there, then maybe this would even have been very, very high because there was no wind blowing on that day. Okay. So this third example is also from air pollution about when to sense. And after following the questions of where to put sensors and what to sense, we now move to this question of when to sense. And here it was not a research question, but more of a money question, that do we keep our sensors running when they are in the bus depot at night? So the buses all come at the depot and rest at night for 4 hours or 5 hours of time. And we wanted to know whether this Airtel or whoever we were paying the 4G bills, should we continue our sensors to keep sending data? And what we figured out was this data, even though all the buses were at the same place at the same time and all should have been reporting the same value, we figured out that this was very interesting for anomaly detection. So for example, here, these are values from different buses, and this particular bus, that sensor had accumulated dust, and therefore it was always reporting a higher value than what its peers were seeing, right? So even though it felt like the bus have already moved across the city, so whatever it is detecting at the depot is not interesting enough, it's just one location. But actually, internally for our system, keeping the system running was useful for anomaly detection. Okay, so this is an example of deciding when to keep sensing versus not. Similarly here, so as I said, my pollution sensors were co-located with the traffic cameras by the police. So what we saw was that I could get these classified counts from the traffic cameras. And here, for example, I'm showing the classified counts on this axis. The number of vehicles are here. The different colors denote the different kind of vehicles which are detected. And this axis is showing the PM 2.5 value. So what we figure out is, even though the traffic is really high between say 9 o'clock to 1 o'clock, which is the morning office hour of for that road, the air pollution is lower at that time, right? But this values start peaking up towards the evening. So what happens here is, because just like wind and traffic were playing a role in the previous here for odd even, here temperature and traffic are playing a dual role. So the temperature is so high that even though the vehicles are emitting and adding to the pollutant, the air is kind of getting rarefied and blowing up. But at night, when the temperature comes down, it all comes down and settles. So people living near the intersection, they might not be facing that or breathing in that pollution during the peak temperature hours, but in winter or even in summer, when at night the temperatures come down, they would be still breathing much higher values than the rest of the city. So this was this notion of delayed correlation, that when to sense, we cannot just keep on saying that exactly at the same timestamp, this is the vehicle count, it doesn't cause pollution, so vehicle does not cause pollution. This cannot be the kind of the deduction, but we need to also adjust this effect of the delays which we see because of other contributing factors like temperature. So these are some questions to ask just using the data itself. And I didn't discuss because many of these works are also done with the machine learning professor, especially Professor Sayan Ranu here, and where each of them is modeled. So even interpolation, forecasting for traffic, for pollution, for any of these data sets, if it is rich enough, we can formulate it as an ML problem and then show, compared to other baselines which existed before, how our accuracy improves or whether our latency is good enough. So I'm not going into each individual problem. Instead, I'm shifting gears and I'm going to another set of problems, especially in privacy and security, which are also very, very interesting. Okay, so this one, as I said, how to ensure integrity of the sensors and the edge computing platforms. This is very critical, and there has been you can check my papers for this because this is just a 45 minutes talk. So there is work on this attestations and remote attestations, either using support from trusted hardware, especially trusted edge hardware. So these are NVIDIA GPU platforms or Intel Atom platforms platforms which we are placing on the bus or on the road or in some public place. And therefore, from this central server or the ICCC, the Command and Control Center, we will have to attest that the software running there is actually the software we have put there. So there is no hacking or other activities. So there has to be hardening. There has to be this white hat tests or red hat kind of penetration testing of the hardware as well as the software, as well as a continuous monitoring of the hardware, and also research wise that like continuously growing research crypto fields of including zero knowledge proofs, how to show computational integrity, how can a platform prove that it is actually running something it is supposed to run. So using trusted hardware reduces the runtime, but maybe many of the edge platforms, they do not come with the trusted hardware support we want. Maybe it has ARM trust zone support, but not maybe ARM CCA support or the confidential compute support. Also not the Intel TDX or AMD NFV kind of support. So what kind of trusted hardware is present and how best can we use it to balance the runtime of the software along with security checks is of high interest. So you can read the papers of my students for this. I will briefly talk about the privacy part because it was kind of fun the way this came up. So when we had put these sensors in the buses in Delhi and Kolkata, this Ola cab company, they expressed interest because they were putting up a mobility center at that point. So they said that the Ola cabs can also be instrumented with air pollution sensors as a kind of a CSR activity, and they can also take part in this. But their main concern was that this location of the cabs, the latitude and longitude values, that is a private data for the company, because air pollution values are not private. So we were not concerned about privacy at all. We said, yeah, of course, we will sense and we will have timestamp, latitude, longitude, and pollution value. This is how, because we need to know where the sensing happened, which is the location of the sensing. So, so for them, the location part, lat long part was very sensitive. And also when I say that we are not giving out raw values, we are not saying that this particular individual cab, Ola cab is sensing this value. We will anyway be doing interpolation, right? So because what we are interested in more is grid wise, every grid of the city should have some information, right? So this is, and we will kind of average out or do a spatio-temporal interpolation on the cab data. So the raw lat long values, those won't be there. But what again we ourselves figured out, but that when we do interpolation, for example, kriging or Gaussian processes is a very standard method of doing interpolation. It gives out also this variance value, right? So it will give out a mean value. So for example, this is the raw sensor values where the sensors were present. And when we interpolate across the city grids, this is how the mean values look like. But then there is also this variance plot, which is kind of giving a confidence, right, for each interpolated or each mean value. And what we see is very intuitive that where sensors are present, the variance is very, very low. It predicts something with high confidence. And where sensors are not present, it has lower confidence, right? So this is much more less in confidence. And this variance plot itself is kind of telling us that actually the cabs were here, right? So it is leaking this information. So what we couldn't work with these private companies because of their concerns, and they were not allowing us to share their data. So instead, what we did was like there was a PhD student who worked on this problem because we figured out that this is a very generic privacy preserving ML problem, PPML problem, where if there are different companies who own this data set, and they might be wanting to training some model as well. So this for other people, this happens in hospital scenarios where they have data. For me, this happened as a concrete case of air pollution data. So for me, if pollution forecasting or interpolation are ML models to be trained, And Ola has some information, Swiggy has some information, Flipkart has some information, whoever has a fleet might be having some information, and they're not allowing us the raw data of that long, right? So, but in privacy preserving fashion, using multi-party computation, can we still train models, was the question this PhD student was asking. And then also when clients are asking these questions, right? So what is the minimum pollution, maximum pollution? If I travel from here to here along this route, what pollution will I be facing? Can those also be answered in a privacy preserving manner without leaking the location of the cabs, or also from the client side revealing minimum information? So this was kind of more researchy PhD kind of work, which came up because we were doing this bus-based sensing, and Ola was interested and then didn't share their data. Like examples of problems is asking whether instead of using cryptography or multi-party computation, can we add differentially private noise, right? DP noise to hide this. So what we figured out is to have any utility. This is not doable because to gain privacy, the amount of DP noise which is to be added is kind of too high, right? So I am building my own low-cost sensors. I'm calibrating them with CAQMS units with a lot of effort. And then just because I want to preserve privacy of some private company, I'm adding noise to the data, which is not kind of what the part we went. So we went with crypto, even though it was a bit heavier, and we showed that it was kind of practical still to do it. Another interesting question came up that when we are doing interpolation, for example, we are taking a lot of different values, and there is an error of interpolation itself. So in one location, I say this is the mean pollution value and this is the confidence level. In another location, I say this is the mean pollution value, the confidence level is very low. Maybe the confidence is 20%. In some location, it is 90%. Now, when a query comes to say what is the average pollution or what is the maximum pollution, then I am dealing with different values with different confidence levels. So some value I say that this grade, the pollution value is 95, but the confidence is only 20. Somewhere the pollution value is 85, but the confidence is 90. So how do we combine values with different confidences was a numerical question. And here also the PhD student and I worked out that this is called the propagated error, that if each value of in a function has certain errors, which I call as the confidence, and the error is just the converse of it. It has some error, then what is the propagated error for the full function's value? If it is average, what will be the overall error? If it's max or mean, what will be the overall error? And each of these we needed to be differentiable because we were working with this in this MPC framework where we needed this piecewise linear kind of function. So this was kind of one more researchy kind of thing. Some more insights, what we figured out is one was the interdisciplinary nature of this kind of work. So when machine learning people, they build models. So here in the first graph, I'm showing some graph convolutional network which is used for pollution forecasting, air pollution forecasting. So accuracy wise, or maybe the converse of it, RMSE wise, these dots here are very close to each other. And even though the models have slightly different architectures with different layers of convolution, different sizes of these LSTM layers. But what we figure out is even though they are very similar in accuracy, their runtime through any MPC machine, this multi-party computation crypto is kind of very different, right? So we figured out that the crypto people versus the machine learning people, they are looking for different objectives, and we need to pick the ML architecture suitably which the ML people might not even care about. They say all of them are of similar accuracy, so pick any one. But from the crypto perspective, it is very critical that something might be doing more number of multiplications, which is very expensive in MPC, right? And so we want to pick a model which does more additions than multiplications. So this is one kind of insight, this ML crypto interdisciplinary part. The other is the systems and compute kind of interactions. So what we figured out that both in machine learning as well as in crypto, some accuracy numbers in their papers might be very high, or in case of even crypto, some protocol might be much better, but an older protocol might have been from a systems perspective very well optimized. So for example, using SIMD instructions, the compilers have done a better job to compile. For example, there was this EMP toolkit which was using the garbled circuit protocol of MPC, and then there was this ABY which was much more recent protocol wise. So the crypto papers citing ABY, they said garbled circuit is old, so therefore you should use arithmetic circuits or Boolean as needed, and you should switch between the computes. So what we figured out, ABY from a protocol perspective seemed to be much more efficient because it was picking the type of operator based on the compute, but the libraries did not use vector instructions, SIMD instructions, and other compiler level directives, which could make a huge difference. So this is the runtime with the older protocol, the garbled circuit protocol from EMP toolkit, and this is a very high runtime of a much newer protocol. So this intersection we figured out because we were working at kind of at the intersection of ML, crypto, and systems, because we had to run these on actual hardware which was on the road, right? So this is something very exciting where the research, the reviewers of the research community, they appreciated this actual insights from real hardware and other compilers. Finally, I'll kind of wrap up within the next 5-6 minutes. So this edge computing is where the platforms that we use, and as you can see, there is a huge range of platforms to choose from. So this is what I'm showing as applications, and I typically work in this traffic domain, and these parts I don't work on. So this blue is something which I work on, and in terms of hardware, it can be a CPU, a GPU. For something which is I'm just prototyping, it can be an FPGA, or sometimes in edge there are also very specialized hardware accelerators. Maybe it has a systolic array or some kind of other chip inside, which does convolutions very fast. Also, there are crypto accelerators and stuff like that, right? So picking the correct hardware matters, because then the appropriate OS, then the appropriate machine learning framework or the crypto framework, and here also different companies come up with their own software pipelines, right? So one of my PhD students completely focused on the GPU, embedded GPUs, and another on FPGAs, and we figured out very complementary things in them because they were working in at the same time, and they were trying to run very similar kind of workloads on their platform. What we figured out that in an FPGA, there also things are becoming very ASIC-like, because even Xilinx, for example, is giving out these DPUs, which are this uh, kind of very fixed cores to run. And of course, I can design my own logic also additionally on the FPGA board. But there was at least more flexibility in terms of this memory interfaces. So how many DPUs which is like a GPU, like the DPU is something which will actually run the machine learning computation. But how many DPUs will be created? How will they interact with the CPU cores on the embedded board? How will the memory ports, the DRAM ports, be configured to work with each of the CPU core, and through the DPU core? These all were configurable and reconfigurable as well. So therefore, we could play around a lot and build very kind of broad understanding of contention, memory contention, CPU contention with the student who was working on FPGA, and have much more direct predictions on runtime of a particular network, or given a similar network, how long will it take to run? So profiling, measuring, and those became much easier for FPGA boards. On the other hand, this is a table of kind of a one of the full sets of hardware at some at a point of time, where we had NVIDIA's edge GPU platforms here, Jetson Xavier here. We now have Orin as well as Thor platforms, which are kind of newer, but this was at that time. And then we also have something from Odroid, which are Intel boards, right? So the CPU in case of the NVIDIA boards are from ARM, in case of Intel boards is from Intel, and then correspondingly there might be a GPU or some other accelerator which is capable of doing a certain function, and then memory and other things, right? So what we figured out was this was much more black boxy, especially this embedded devices which come with accelerator or even an NVIDIA GPU. There is no way as a programmer or as an application developer I can play with memory ports or how things are mapped in the hardware, right? So this is some black box, and even the CUDA drivers and everything is also closed source. So there is no way of understanding what is going on, how is the actual workload getting mapped into the hardware. So we did some interesting measurement studies, and I'll just quickly say some counterintuitive observations here, because the intuitive observations are less interesting. So here I give an example of a Xavier NX board, which is smaller and also less costly. So it has 384 GPU cores, and the AGX board had 512 GPU cores. The number of SMs or symmetric multiprocessors are also lower here. Similarly, the tensor cores were lower here, and this actually was half the price. So this was around 60,000 and this was around 1.2 lakhs. So this is how the boards were. And what we figured out is when we compiled a certain model, for example, a machine learning model, Inception V4, and we compile it on the AGX board. By compile, I mean there is a pre-trained model with some weights, and this is converted through the TensorRT engine into actual software which can run on the GPU. So this is compiled on the AGX and run on the AGX, and this took 42 milliseconds to run. Whereas if it was compiled on the smaller board and run on the smaller board, it took 31 milliseconds. So this is very, very counterintuitive that a bigger board with more SMs and more CUDA cores is actually taking longer time to run a certain workload, right? And this we saw in many cases. And the main reason for this was this hand written kernels, CUDA kernels, which at that point NVIDIA was doing. So as hardware grew, some human had to figure out what should be the matrix multiplication sizes. And they were not able to keep up and keeping up with more and more kernels to fit bigger boards more aggressively. Right. So this was like the human written library functions were more suitable for the smaller board, and the same ones, when we used on the larger board, they were suboptimal. They could have run a bigger matrix multiplication there, but there was no suitable kernel library function which was available, right? So these were certain insights which we gave also a talk at NVIDIA itself. The other, this one I'll skip here because of lack of time. This one also was kind of interesting. So here, this particular, so this one actually I'll just talk about this lower table, not the above one. So what we are seeing here is change in the output given the same input. So when I say engine, it's a pre-trained model, and the TensorRT has converted it for a particular hardware board. So I compile it once, get engine 1, compile it again, I get engine 2, and again compile it the third time and get engine 3. Now the expectation is, because the model weights are the same, it's the same pre-trained model. If I give it some input, it should give me the same output, right? But what we figured out that out of 500 images, a lot, almost like 269 images actually changed its output just because of this compilation process which TensorRT was doing. So the same pre-trained model weights are not changing. It has seen the same training data, but because of the way the engine was built, so this engine building included model compression, then it included maybe fusion of certain kernels, then mapping into actual CUDA library functions. So these are typical steps in the TensorRT pipeline and in any neural compiler pipeline. We figured out that because of these steps, a lot of images were giving a different output, right? And so we figured out why this happened, and this also we communicated to NVIDIA. And we figured out using some other academic tool, which was TVM, and this we saw that this was more because of accumulation of floating point errors. That when we checked the TVM code, of course, the NVIDIA TensorRT code was closed source. The TVM code, what it does is it computes some unoptimized function using just Python, and then it actually does the checks the TVM compressed compute. So if I'm doing quantization, if it is doing layer fusion, whatever it does, it first checks the output without doing it and then with doing it, and then figures for correctness. So it says that whether these two has a certain kind of threshold precision, they match within that, and then only that optimization is accepted in the engine. So this was a good thing about TVM, which did not have any change in output, whereas TensorRT was not doing this, and as a result, it would keep on accumulating this FP error, and as a result, at the last layer, which is the softmax layer, the probabilities which will flip between the highest class and the second highest class as the entire result of all the computation errors accumulating, and then we will get a different output given the same input. Okay, so this was also some counterintuitive observation. And the last one was this runtime itself. How long does it take to run a model on an NVIDIA board? We thought that NVIDIA's engine will win here, but what we figured out was the open source engines did much, much better. Because at least at that point, AutoTVM and AutoScheduler were using ML-based compilation. So it would not use handwritten kernels, CUDA kernels. Instead, it will ask the ML-based compiler to search for the best CUDA kernel. It says it will be a for loop, use styling and some of the parameters, but the parameter search was entirely automated. So it would come up with something which fitted the hardware much, much better. So the compilation process will take longer. AutoTVM will come up with actually an engine for a model in a longer time than TensorRT, but then it will actually be a small fraction of the time. So this was the counterintuitive observation 3, that a generic NN compiler, it outperforms the NVIDIA specific neural network compiler. And there is also a lot of work on thermal. So you can check my web page for also a recent paper here that because I'm putting these embedded GPUs on the road, and in Delhi, at least the temperatures go up to 45 degrees Celsius, and I'm running these GPU workloads there. So therefore, how do I build a shim layer or a control layer for thermal safety? Because otherwise, earlier when the Vehant or Abmatika were just putting, so they would have very good accuracy models. They will train the models, they will deploy it, but then the hardware will start rebooting, right? So it was not safe hardware, and after a while, it will just we can brick the hardware also. So this is where my group has given safety or control software, where instead of DVFS kicking it at every point and allowing that board temperature to go to 60 degree and 75 degree, we proactively control how many threads the GPUs should run, or what should be the GPU frequency. And sometimes we do it in application aware fashion. We know what is going on in the road. We can check on the CPU itself using background subtraction or some like kind of lightweight thing, and then control the GPU in an appropriate fashion. So please check my papers for more details on this. So yeah, so I'll conclude the talk here that these are the kind of different threads in which my group is working. And also feel free to call. So these are the students who have already graduated. And I mean, most of them are working in kind of architecture kind of companies now, because this is where the edge compute platforms from ARM or from NVIDIA or from they played a role, and so that's where they went. And Sachin was more on working with the data, so he has now gone into work with more data from this Red Cross and Heidelberg University. So yeah, I'm happy to take questions at this point, and yeah, feel free to ask questions.
Thank you very much, Professor, for delivering such an interesting talk. And we are sorry that you had to take the talk during your
And no issues. Yeah, I didn't want to cancel. Yeah, but I'm sorry I coughed so much. Yeah.
No. That's totally fine. Also, if audience, please feel free to post any questions or ask any questions here. Yes, Preeta, please.
Yeah, so yeah, we appreciate your continuing with the talk despite your illness. One question, have you also looked at the problem of using inexpensive, unreliable sensors or swarms of sensors when they're either uncalibrated? Suppose you use
Hmm.
something one-tenth the price, and even if you have to put 2x the number of sensors, if you could use some data analysis or some of the model based predictions to see which readings to keep or which sensors to keep and which sensor data to discard, especially when the sensors are not calibrated.
Yeah, I think that's a very, very nice direction. But unfortunately, I have always been given some money from some organization, and they wanted to have at least some level of reliability. So this, even the air pollution sensors, I had to calibrate them, but at least I had to even select from the China-based ones versus some European-made Alpha Sense ones, so that at least in the same batch, if I buy 100 sensors and I keep them on a table, they report the same values. So there is no drift across the same batch of sensors. So this I had to maintain because of the requirements. But what you are asking is also very interesting from a research perspective. And I mean, there are certain chances, I would say, but in not here. So there are this now a lot of traffic, this in-vehicle sensing, which is also happening, and they are actually coming from very different companies. So this there is kind of a standardization issue, where there is accelerometer or gyro, and so Zen Drive, which is based in Bangalore, they were asking about exactly this. So one is simple mobile based monitoring, which has always looked at this. So they were asking me that in Mobisis or this community, each mobile phone has a different hardware. So there is even, so they will all report very different values. But then if the insurance company has to check if the driver is driving well or bad, then there has to be certain standards to be met. So there is a real research question which I have not looked at till now. But I mean, we can talk, and I also need to think about exactly how to do this. So as you are saying, there will be some statistical pattern that if something is always driving on the same roads, for example, a large set of drivers, and everyone sees some dip there. Maybe the dip values are different, but we understand that there will be a bump or something there, which is actually like kind of seeing up. So the relative values even we need to check instead of maybe checking the absolute values. So in certain cases, this should definitely be possible, or and deciding the threshold and having enough statistical data samples will be very critical. So I'll discuss, because Zendrive seems to have a lot of like just normal cars with phones, and they are working with this automotive insurance kind of companies. So that's a real problem for them. But for me, the scale of data was never like this. Where I could have a lot of data to be statistically finding a signal among very noisy ones. So I'm sorry, I've only worked with a bit more reliable and more costly low cost sensors. Yeah.
Mhm. Yes,
Mm.
thank you.
Other questions?
No, Professor. Even
Okay.
in chat as well, there's
Okay. Okay.
no
Okay.
questions.
Yeah.
And thank you
Sounds
once
good.
again.
Thank you very much for giving me this. I'll see you when I go to IIC sometime for visiting.
Sure,
Thank you.
Professor.
Bye.
We'll be
Bye.
happy to see you again, meet you
Bye.
again.
Bye.
Okay. Also, thank you all audience for attending, and have a great evening. Thank you.